Hello, everybody. Let's do solutions and common mistakes for this modeling problem. A lot of people, well, this was a lot more challenging, I guess, for people than I expected it to be. But that's okay. You know, it's never too late to learn. So consider this your opportunity to learn the things you didn't get about the problem. We are modeling the horizontal position of the circled car as the Ferris wheel rotates counterclockwise, which is this way, at a constant rate. So right away, if I'm thinking horizontal position, if I'm just visualizing this, the horizontal position starts at the smallest horizontal position, rotates around to the largest horizontal position, and back to the smallest. And in part A, 0, 0 is located at point A. So this would be 0, 0. So it seems like I'm oscillating horizontally around 0, 0. A lot of the thinking in class was about connecting the equation, which you're trying to get, to the scenario, but also connecting it to the graph, because that can help you check to make sure that the things that you're doing make sense. So if I was going to graph the horizontal position here, let's sneak this in here. Here's time, here's horizontal position. So this is at time 0, it's up here. So at time 0, I'm located here at my smallest horizontal position at negative L. How do I know it's negative L? This was 0, 0. I said that the length of this beam is L, but because it's to the left, it should be negative. And as I rotate around, eventually I'll get around to this point over here, which should be a distance of positive L. So if I'm graphing it, it looks like this. One of the things you always have to decide if you're modeling an oscillating motion is, does it make sense for it to be sine or cosine? Here, this looks like it should be cosine, except it's a cosine that's been flipped upside down, because regular cosine would look like that. Here, we're starting from our smallest point. So far, we know we should have opposite cosine of something. It looks like the amplitude here is L, because I'm starting at negative L going up to positive L, so it's half the height of my full wave, or half the diameter of my oscillation. I don't want a midline, or rather the midline is 0, because I'm oscillating around 0 in the middle here. And so the last thing I need to do is figure out what my rotational rate is. So it said that it takes me 10 seconds to get from this point down to that point down here. So if a quarter turn takes 10 seconds, a half turn will take 20, 3/4 will take 30, and then a full turn will take 40 seconds. So it takes me 40 seconds to get all the way around. So what that means is that my full wave here takes 40 seconds. Remember that that's the period, because it's the length of my wave, but the period doesn't ever appear in the equation. Instead, it's the frequency. So the frequency is going to be 2 pi over the period, which is just pi over 20. So this could be pi over 20t. Okay. So now let's go over a couple of misconceptions. So some people decided to put a plus h on the outside here. The reason that doesn't really make sense is hopefully clear by now. If we're paying attention to what we're actually trying to write an equation for, we're interested in the horizontal position, which is just how far back or forth the circled car has gone. H is in the opposite dimension. H is the vertical position. And it's not the vertical position of the car, it's the vertical position of the axis of rotation here above the ground. But yeah, so because it's vertical, it doesn't really play any role at all in the horizontal position of the car. You can also see that if we'd graphed the horizontal position of the car, like I was saying, the midline is around 0 because I'm oscillating around a horizontal position of 0. So it wouldn't make sense to shift this graph at all. Another thing that people got a little bit messed up with the fact that I said, let's define theta this way. My defining theta this way was relevant to part B of the question, but it wasn't really relevant to part A. Because in part A, all I'm interested in is modeling the horizontal position of the car. But you don't have to, your equation here, see how there's no theta in my equation? I only have t. I only have time. So what do I want to say? So a lot of people were trying to make their equation both fit. So like for a particular time, they wanted the angle here to match the theta there, and they wanted the output for their equation to match the horizontal position. But as you're going to see, that's a little bit trickier to get both of those to happen at once. And we don't really care about having both of those happen at once, because the only thing we really care about is horizontal position. So you can see that if I plug in different times to this equation, it's going to give me the horizontal positions that match the scenario. People who are trying to make the inside angle match that theta, their thinking, which was really, really great thinking for part B, they said, okay, look, I know at time equals 0, the angle here is at negative 90 degrees. So let's work in radians. So at time 0, our angle is at negative pi over 2 radians. And we already know what the rotational rate is. So they said, look, let's do this. Let's do cosine of negative pi over 2 plus pi over 20t. And then they did various other things on the outside here. So let's keep it this way. Let's double check to see if this makes sense by plugging in a time. So at time equals 0, I plug in 0. This term becomes 0, so my angle is negative pi over 2. So they've done a great job of making sure that the angle matches the picture. The problem now, though, is for an angle of negative pi over 2, if I take the cosine function, that's going to give me, let's imagine cosine pi over 2, or negative pi over 2. So negative pi over 2 in a cosine function is defined as that point right there. So cosine of negative pi over 2 is going to be 0, because there's no back or forth. So what that means is at time 0, this angle matches the angle I've defined here, but that doesn't magically change how cosine works. So cosine of negative pi over 2 still has 0 as its value. And so that would predict that my horizontal position is 0. But my horizontal position doesn't actually start at 0 when time is 0. So I think that was the confusion. The idea that if I want to choose to think about the angle here, that doesn't change how the cosine function works, and you still want to be modeling horizontal position at the end of the day. For people who did this, it wasn't a very large deduction. It was because you were doing something sort of reasonable. You just didn't check to see, did it actually make sense in your scenario? But that was definitely an issue that cropped up for some folks. Okay, let's move on to part B. Part B says, write a model for theta as a function of time. So we want to know, how does the angle change as a function of time? So the trick here is to realize that, so I was trying to test to see, did people have kind of a basic intuitive understanding of what the motion actually was in this scenario, or were they just trying to mimic things we'd done in class? Because in class, I never actually said, let's write an equation for theta. But the whole time we've been doing this stuff, we've been talking about rotating at a constant rate. So hopefully your thought was, okay, if it's rotating at a constant rate, that means theta is changing at a constant rate, so it should be a linear function. If we draw a little picture here, here's time, here's theta. Again, let's work in radians. So the way that I've defined theta here, at time equals 0, theta is negative 90. So here we are at negative 90, which I'll do in radians at negative pi over 2. We know that 10 seconds later, the angle has gone, or the car has gone down to this position, down here, which I defined as an angle of 0, because it hasn't displaced at all left or right. So it's a linear function that looks like this. I mean, we could resolve this all over again, but we've already done this in part A. Like, you already solved that the rotational rate is pi over 20. But you could, if you were thinking about it as a fresh scenario, we could do it all over again. So if I'm writing a linear equation, we've got the y-intercept here, at negative pi over 2. This is going to be change in y divided by change in x. So change in y is change in angle. So we've gone up by pi over 2. And the change in x was 10. So that's our variable time. So pi over 2 divided by 10 is just pi over 20, which is the same thing that we got in part A. So that would be a great answer. The thing that I was looking to see was, were people going to say, oh, this is modeling under sinusoids, I must have to write a sine function, or I must have to write a cosine function, because that's what you do. Remember, a big theme in my class is don't write stuff down just because you remember doing that in the past when you see certain keywords, like modeling or rotations or whatever. Don't try and mimic without knowing what you're doing. The way you solve the problems is the same every time. What you do is you ask yourself, what information is the problem asking for? It's asking for an equation that tells me the angle at certain times. And so then you ask, what do I know about that? And what you do is determined by the information the problem wants and things you know about that information. So if you know that theta is changing at a constant rate, you know that means linear function. If you were imagining going around a circle at a constant speed, you should say linear to you. So anyway, my point is, I'm looking to sort of like check to see kind of who's mimicking and who's trying to understand kind of what's going on and like really visualize it for themselves. Okay, so the last part of the problem, let's read it, or hold on. Okay, through the magic of paper, now we are seeing it all at once. There we go. So, new scenario. Now we are assuming 0, 0 is located at the observation deck on point B. So, this is the new 0, 0 point. Which means that the point, and the observation deck B is located at a distance q to the left. So if this is the new 0, 0, this distance q is now to the right of 0, 0, which means this point A is now located at distance q to the right. Which means this distance here was L, because the distance from here to here is still L. So that means this point way out here is L plus q. And the distance to here would be L minus that q. Except it's negative. So negative. Well, hold on. Let's think about this. So I was just about to write negative L minus q, but that doesn't make any sense. Let's figure out like how do you get to this distance here. We know that that distance is positive q. We know that this distance is L, but we're subtracting L. So if I go, let's imagine going this way by Q, and that, so I'm adding Q and I'm subtracting L. That gets me that far. So I think this makes sense as Q minus L. And if all of that is too hard to think about with letters, I totally welcome you to think about it with numbers all the time. So if this was 10, and that was 2, and this is 0, it would make sense that 0, like this would be location 2. Location negative 2 would be over here somewhere, but if L is 10, this should be location negative 8, because if I'd gone 2 this way and 10 that way, that takes me to negative 8. Okay, anyway, so now we've got coordinates for the horizontal axis there. So now I've got that the Ferris wheel is rotating at the same speed as before, but now when we start measuring at time 0, we don't know where the circled car is. All we know is that 2 seconds later at time t equals 2, it's at point A. So what I'm imagining is at t equals 2, the car is here. Because it's rotating counterclockwise, at t equals 0, it was somewhere over here to the left, but we're not too sure where. And maybe you could find out where. So it's over here somewhere to the left, and it's rotating, and at t equals 2, we hit that point, and we're going to continue to go around. Okay, so again, let's try and we're still modeling horizontal position. So let's try and use a graph to think about the information we know here. So because I don't know the horizontal position at time 0. And I could set myself a goal of trying to figure out what the horizontal position is at time 0. And you could definitely do that. We know the rotational rate. So if we think at time 0, it's here, that would mean theta is 0. So we could go backwards and we could say 2 seconds earlier, let's figure out what the theta was. And then once you know what the theta is, you could calculate the horizontal distance. But before diving down a particular solution route, maybe we don't even need to know where the starting horizontal position is. So if I'm making a graph, again, let's make this time, this horizontal position. Let's call this 2 seconds. I know that at 2 seconds, the horizontal position is here at the midpoint. Because the horizontal position is still oscillating back and forth around the middle of the axis of rotation. Except now I've moved the coordinates to here. So right now I'm oscillating back and forth around this value q. Again, maybe it's helpful to think about this in terms of numbers. So let's imagine this distance is 2 in some appropriate units, maybe meters. It's more than 2 meters. Anyway, let's imagine this is 2. So here I'm starting at the leftmost horizontal position. Eventually I'll get to horizontal position 2. Then I'll get to some largest horizontal position, and then back to 2 again. So I'm going to be oscillating around 2. I know at time 0, I'm at that horizontal position. And then as time increases, I'm going to be going positive and negative. So it's sort of like this. This is what the graph looks like. I'm going from Q to a larger horizontal position, back to Q, and then to here. And because the rotational speed is the same, we still know that this is going to take, 40 seconds? So this is to 42. So that period hasn't changed at all. The only thing that happened was it got shifted in time, because we know that 2 seconds is where one of the key locations was happening. We also know that because the location of 0 on the horizontal axis shifted, that means the vertical axis here shifted, because the vertical axis here is our x-coordinates. And that's very similar to stuff we've done in class. What are we missing here? All right, so we've got as an equation so far that we need a plus q on the outside. We should decide sine or cosine, but just looking at the picture, I'm thinking let's use sine, because that looks like a regular sine wave. So let's do sine. We know it's been shifted, and then we know what the rotational rate is. And again, you can plug in individual times to kind of check that this makes sense. If I plug in t equals 2, 2 minus 2 is 0, which gives me an angle of 0. Sine of 0 gives me 1. Nope, 0. Excuse me. Sine of 0, sine tells me the y-coordinate, so it gives me 0. And so then if that whole thing is 0, I'm just adding q as my horizontal position, and lo and behold, there I am, horizontal position q. So that makes sense. So the only thing that's missing is now I've got amplitude L. It wouldn't make sense to make this negative here, because if I made this negative, that would flip my graph upside down. So hopefully the thinking process here is clear. It's the same thinking process that I tried to outline in class. There's a scenario. You need to write the equation, but it's very hard to jump straight to the equation because there's a lot happening. So what you need to do is use the graph as a thinking tool. You need to make connections between what you know is physically happening, what's going on in the graph, and use those two things to help you think more clearly about what should be going on in your model. Okay, I hope that this was helpful.